All right, class, welcome to this video on the AP Statistics Chapter 3 test. We're going to go over one of the versions of the test, and hopefully this will be useful for you. So number one, it says, other things being equal, larger automobile engines are less fuel efficient. You're planning an experiment to study the effect of engine size in liters on the fuel efficiency in miles per gallon of sport utility vehicles. So we see here that other things being equal, larger automobile engines are less fuel efficient. So the bigger the engine, the less the fuel efficiency. And it says in this study, which one is the response variable and which one is the explanatory variable? Well, in this study, the explanatory variable is the automobile engine, as that is going to help us predict the fuel efficiency. And the fuel efficiency, or the gas mileage, in this case, it's talking about the effective engine size on the fuel efficiency. The fuel efficiency is the response variable, okay? And so we know that as the engine gets bigger, right, as the engine increases in size, we know that it says that the fuel efficiency, the fuel efficiency is going to go down, right, as the engine gets bigger. So this is going to be a negative association, right? As X gets bigger, Y gets smaller. So gas mileage is a response variable. That's true. You expect to find a negative association. That's true. So the answer is A. Number two. In a statistics course, a linear regression equation was computed to predict the final exam score from the score on the first test. The equation is given here, where Y is the final exam score and X is the score on the first test. Carla scored a 95 on the first test. What is her predicted score value on the final exam? So all we got to do is plug in 95 into the equations. We get 10 plus 0.9 times 95. All right, and so we got 0.9 times 95 plus 10. You do that on the calculator, you get 95.5 approximately. So that's going to be her score on the predicted score on the final exam. All right, in the course described in number 2, Bill scored a 90 on the first test and a 93 on the final exam. What is the value of his residual? So the residual is Y minus Y hat, right? So first off, we need to figure out, it says his Y hat, he scored a 90 on the first test and a 93 on the final exam. So since he scored a 90 on the first test, we need to calculate his predicted score on the final exam. This is his actual score on the exam, so we're going to call that Y. But we want to find the Y hat. So we got 10 plus 0.9 times 90, and that's going to give us his Y hat to be 91. All right, so now he's got a predicted score of 91, but his actual score is 93. So his residual is equal to Y minus Y hat, and so his Y is 93, and his predicted was 91, and so he has a residual of 2. So the answer is B. Okay, the correlation between the heights of fathers and the heights of their fully grown sons is R equals 0.52. This value was based on both variables being measured in inches. If fathers' heights were measured in feet and sons' heights were measured in furlongs, the correlation between heights of fathers and heights of sons would be what? So in this case, remember that correlation does not depend on the units. So it does not matter what the units are, a furlong, a mile, inches, whatever. It's still going to not change the correlation, okay? So in this case, the correlation is still going to remain unchanged. It's just a conceptual question. So the answer is C. All but one of the following statements contains an error. Which statement could be correct? So, all right, so it says there is a correlation of 0.54 between the position a football player plays and his weight. So if you look at this is incorrect because the position a football player plays, for example, quarterback, wide receiver, whatever, that position, that's a categorical variable. This is a categorical variable. And correlation is only good between quantitative variables. You can't have correlation of a categorical variable with a quantitative variable. It has to be two quantitative variables. Okay, so it's between two quantitative variables. All right, so it can't be A. That's incorrect. Part B, we found the correlation of negative 0.63 between gender and political party reference. Again, that's the same thing. Gender, political party reference, those are categorical variables, right? So it can't be that one. The correlation between the distance traveled by a hiker and the time spent hiking is 0.9 meters per second. This is incorrect because R does not have any units, right? R is unitless. So this is incorrect. All right, so it cannot have any units. Part D, we found a high correlation between the height and age of children. R equals 1.12. Well, R cannot be greater than 1, so this is incorrect. And the correlation between mid-August soil moisture and the per acre field of tomatoes is R equals 0.53. So R is correlation between two variables, which are both quantitative variables, so this makes the most sense. All right, number 6, a set of data describes the relationship between the size of annual salary raises and the performance ratings for employees of a certain company. The least squares regression equation is given, so y hat equals 1400 plus 2000x, where y is the raise amount in dollars and x is the performance rating. Which of the following statements must be true? All right, so for each 1 point increase in performance rating, the raise will increase on average by $1,400. So if you look at the equation here, this is the slope, right? So 2,000 is the slope. And the y-intercept is 1,400. And so remember that the slope tells you the change in y over change in x, right? So this is 2,000. This is saying that you're going to have a change in the y value of 2,000. So this is going to be $2,000 for. There's going to be for a raise of $2,000 for every increase, for every 1 unit increase in the rating. Okay, so for every 1 unit rating, there's going to be an extra $2,000, okay, for every 1 point increase in the performance rating. All right, so this is incorrect because this says for each 1 point increase in the performance rating, the raise will increase on average by $1,400. They used a y-intercept here, not the slope, so this is incorrect. The actual relationship between salary raises and performance rating is linear. Is that true? And this is not necessarily true because it says the actual relationship is linear. All we know is that there's a least squares regression line, but we have no idea whether it's actually linear or not. Remember, what helps us determine if it's linear or not is the scatter plot, as well as if you look at the residual plot to see if it should be linear, right? So you have to actually look at the scatter plot for this. You need to look at the R value. There's a lot of things you got to look at, right? But for sure, we don't have any information on that. The residuals for half the observations in the data set will be positive. Again, we don't have any information on the residuals being positive or negative. This is not necessarily going to be the case, right? It depends on the model that in the data. The correlations between salary raise and performance rate is negative. In this case, no, it's actually positive because if you look at the regression equation, it's a positive 2,000. So the slope is positive. So this is actually a positive least squares regression line. So we would expect that the correlation would be positive. If the mean performance rating is 1.2, then the mean raise is $3,800. So let's see if that's true. The mean performance, so the mean performance is X bar, so that's 1.2. So if X bar is 1.2, then Y bar must be 3,800. Is that true? Well, let's plug it in. So let's plug it into this equation. So we get 1,400 plus 2,000 times 1.2, and 1.2 times 2,000 is 2,400. So we get 1,400 plus 2,400, which is 3,800. So this actually holds true. The X bar and the Y bar are on the regression line, and it looks like that is true. Okay. So it's got to be E. All right, number 7. A least squares regression line for predicting weights of basketball players on the basis of their heights produced the residual plot below. So we got our residual plot. What does the residual plot tell you about the linear model? Okay, so if you look at the residual plot, there appears to be some kind of curvy pattern, right? You can see that. It does not appear to be random, in other words. It appears to be curved, okay? So in this case, since there's a curve pattern, that means that the linear model is not appropriate, okay? You do not want to see curve patterns or anything like that in residual plots if you're looking for appropriateness of linear models, right? So residual plot is not an appropriate means for evaluating a linear model. That's just false, right? So remember, residual plot is helpful to determine the appropriateness of a model, right? But so it's not not telling you whether it's evaluating the model. It's just saying that that the residual plot helps you determine if the linear model is appropriate. Okay. Part B, the curve pattern in the residual plot suggests that there is no association between the weight and height of basketball players. And this is not necessarily true. So we want to see, what does the residual plot tell you? So this is saying that there is some kind of association, but there's a pattern to it, and there's a curved pattern to it, right? So we see that there's some kind of a curved pattern, but it doesn't tell us that there's no association. It tells us that the linear model is not appropriate. So it's not that one. The curved pattern suggests that the linear model is not appropriate. That's what the residual plot tells you. So that has to be the answer. All right, so use the following to answer questions number 8 and 9. One concern about the depletion of the ozone layer is that the increase in UV light will decrease crop yields. An experiment was conducted in a greenhouse where soybean plants were exposed to varying levels of UV measured in Dobson units. At the end of the experiment, the yield was measured in kilograms. A regression analysis was performed with the following results. Okay, so the least squares regression line is the line that does what? So the least squares regression line. This is a conceptual question here. The least squares regression line, remember what that does is it minimizes the sum of the squared residuals. This is basically a definition of what is least squares regression line. It minimizes the sum of the squared residuals. So which one has that? Minimizes the sum of the distances between the actual UV and the predicted UV. So remember that the response variable is the yield. These are the explanatory variables, so that's not correct, okay? And it's not the sum of the distances, right? It's the sum of the squared distances between the actual and predicted, and it's not UV values, it's the yield, okay? So the least squares regression line gives you the sum of minimizes the sum of the squared distances in the y, okay? It minimizes that. All right, so minimizes the sum of the squared residuals between the actual yield, that's the y is the actual yield, and the predicted yield, that's the y hat, right? That's what we're looking for. The sum of the squared residuals of that. So yes, that is true. Minimizes the sum of the distances between actual yield and predicted UV? No. Minimizes sum of squared residuals between actual UV and predicted UV? No. Minimizes perpendicular distance between regression line and each data point? No. So the best answer is B. Which of the following is correct? If the UV value increases by 1 Dobson unit, the yield is expected to increase by 0.0463 kilograms. So let's take a look. What is the based on this, what does the regression line tell us? Well, it says that according to this, the estimate for the constant, so that's your A, and the UV, that's your this value is B. Okay, so y hat equals A plus bx. So y hat equals 3.9800, of course, minus 0.04629x. Okay, so that's your regression equation. And this is your slope. And so that's saying that there is a decrease. So for every 1 unit increase in the x value, which is the UV value, which is the Dobson unit, there is a decrease of 0.04629 in the yield of kilograms, in the yield of the plant, right, of the soybean plant. So that's what it says. So if the UV value increases by 1 Dobson unit, the yield is expected to increase? No, it's decrease. So it's not A. If the yield increases by 1 kilogram, the UV value is expected to decrease? Nope. If the UV value increases by 1 Dobson unit, the yield is expected to decrease by 0.0463. Yes, that's the right answer. All right, which statements below about the least squares regression are correct? So this question is only for 8 and 9. Okay, so this 10 is separate. So which statement below about least squares regression are correct? Switching the explanatory variable and response variables will not change the least squares regression line. So switching the explanatory and response variable will not change the least squares regression line. That is false. If you change x and y, that's going to change the y hat equation. Okay, so that will change this equation if I switch A and B, or x and y, the explanatory and the response. So this is incorrect. Statement 2, the slope of the line is very sensitive to outliers in the x direction with large residuals. Yes, so if I have a regression line that looks like this, and I have an outlier that is large in the x direction, for example, and it has a large residual. So for example, like this, it's very far away in the x direction from the data, and it has a large residual. Then that's going to change the slope, and it's going to make the slope change dramatically, right? It's going to actually make the slope go like that, the line go like that. It's going to swing the line that way and that way. So that's true. A value of r squared close to 1 does not guarantee that the relationship is linear. That is true. So r squared being close to 1 does not guarantee it's linear, because you could have a situation where the r squared is 1, but the relationship is not linear, right? So for example, you could have something that looks curved like that, but if I do the line, this line, this r value for this line, this r squared value is very high, might be 0.99, for example, or 0.98. It's close to 1, but the data is not necessarily linear. The best model would be a curve, right? So you just got to be careful with that. So both 2 and 3 are true. So the answer is D. All right, so this is going to do it for the multiple choice part. Now we're going to look at the free response. So part 2, a certain psychologist counsels people who are getting divorced. A random sample of 10 of her patients provided the data in the following scatter plot, where X is the number of years of courtship before marriage, and Y equals the number of years marriage before divorce. By the way, when you're doing the notes for this video, you're basically going to write explanations of, basically what I'm discussing. Okay, so I'm not necessarily going to write a whole bunch of stuff for the multiple choice, but you should absolutely be explaining why the answer is the way it is and why certain answers are not correct. Okay, so you should absolutely be explaining all of this as part of your assignment if you're doing the corrections. All right, so let's look at, so it says number of years of courtship before marriage, y equals the number of years of marriage before divorce. So here's our scatter plot. Describe what the scatter plot reveals about the relationship between the length of courtship and the length of marriage. So in other words, they're talking about describe the scatter plot. When you describe a scatter plot, you want to talk about strength. You want to talk about direction. You want to talk about form. You want to talk about unusual features, right? DFSU, direction, form, strength, unusual features. These are the things you need to talk about. Now, there are no unusual features in this graph, in the scatter plot. There's no outliers that I see. It looks pretty moderate. Look at the linear relationship. So the form is linear. The direction is positive. It's going up. The strength is moderate, I would say. And then no unusual features, okay? So this is what we're going to talk about. Okay, so for part A, we're going to say, okay, so there appears to be a moderately strong positive linear relationship now you got to talk about the context between the length of courtship and the length of marriage. Okay, and there's no unusual features, so we don't have to necessarily include that, but we can, I can include that here. That does not appear to be any unusual features such as outliers. Okay, so there's part A. Part B, suppose a new point at 4.58, that is, years of courtship is 4.5, years of marriage is 8, were added to the plot. What effect, if any, will this new point have on the correlation between courtship duration and marriage duration? Okay, so let's go ahead and include that, 4.5 and 8. So 4.5 and 8 would be, this is 4.5, and 8 would be down here. Okay, so it would be like a point like that. So if I did add that, what's that going to do? Well, if most of our data is here, right? If that's where the average is, rather. When I say most of the data, I mean the average. If the average of the data is here, then notice that this is far away from the X bar, the average and the X values, right? And it also is far away from the line. So we have a high residual and we have an outlier in the X direction. A horizontal outlier, I guess you can say. Okay, so that's going to change the graph. It's going to make the graph go like this. It's going to make it swing down and up on the left side. And so that's going to change the slope, okay? So and then that would also decrease the correlation because now this is far away from the data, right? So they're actually asking, let's make sure we answer the question, what will it have on the correlation? Okay, so they're not asking for what effect will it have on the equation or the line, but it is asking for what the correlation is. So because this is an outlier, it's far away. It's high leverage, things like that. So that means horizontal outlier. it strays from the data, it's going to decrease the correlation. It's going to make it worse, right? So the correlation is going to decrease because the point strays outside the linear pattern. Of the other points. Okay, thereby weakening the association. Between the two variables. So it's going to weaken the relationship between duration and coefficient duration and merit duration. Okay, so next. So that's it for that part. So now for part C, it says below is the computer output for the regression of length of marriage versus length of courtship. So what is the slope of the regression line? Let's write the regression. Let's write the equation of the regression line here, by the way, just to practice it. So the constant, this is A. Courtship, that's the coefficient, is B. So the equation is 5.710 plus 2.4559x, okay? So there's our equation. This is your slope, all right? So some students had trouble identifying the slope for whatever reason. The slope is the 2.4559. S is not the slope, okay? S is the standard deviation of residuals. That's completely different. That's something different, okay? That's actually what they're talking about here, where they're asking about. Okay, so for part C, the slope is equal to 2.4559. And so we want to interpret, okay? So interpret the slope. So remember, this is over an invisible one. So let me just show you my work here. This is over an invisible one, right? So, and the units for y, the units for y are, if you look at the here, this is y and this is x, right? So it's the increase in the y is marriage and x is courtship, okay? So for every 1 year increase in courtship, there's a increase plus 2.4559 years in the marriage. Okay, so that's what it's saying. And that's what we're going to say. So for each 1 year increase in the length of courtship, there, or we can say the predicted, keyword is predicted, the predicted length of marriage increases by 2.4559 years. Okay, so there's my interpretation of the slope in the context of the problem. All right, explain what the quantity S equals 2.474982. That's the standard deviation of residuals. Okay, so a lot of you guys said that that was quite a few of you guys said that that was a slope. That is not the slope. Okay, explain what this measures. Okay, so what this measures, what the standard deviation of residuals measures. Here's the formula for the standard deviation of residuals, by the way. Is the square root of the sum of the residuals squared divided by n minus 2, right? So there's your formula for the standard deviation of residuals. And what this does, it measures the average residual. It measures the average error in my prediction. Okay, so if my prediction on average is off by 2, then that's what the standard deviation of residuals is saying, okay? In this case, our average error of prediction is about 2.74982. Okay, so let's go ahead and write that. So for this, we're going to say, when using the regression line, so when using least squares regression line, the predicted, or I guess we could say when using the least squares regression line, we will be typically, I could say we will be typically, or on average, so I'm going to put in parentheses on average. I put by, so to say B. We will be typically, or on average, off by about 2.749. So we will typically be on average be off by about 982 years. Okay, so that's what that means. So on average, we're off by our prediction. Our prediction is off from about 2.7449 years. Okay, so part E. The psychologist is curious about whether having children has an impact on this relationship. She draws a second scatter plot with those couples who have children as open squares and couples without children as closed squares. So they want you to comment on the impact that having children has on the relationship between the length of courtship and the length of marriage for these patients. Okay, so if you look at the ones with children, it appears that they tend to have longer courtships, right? Like, for example, this one, no children, short courtship, right? Not many. These are, like on the smaller end, right, of courtship and years. But those with children tend to have had longer length of courtship, and not only that, also longer length in the marriage. So that's interesting to note. Okay, so we can make a note of that. So it appears that couples with children have longer courtships and longer marriages. It also appears, so if you look at the correlation for the closed dots, the no children, it doesn't seem to. I mean, there's a correlation there, but doesn't seem to be as strong. But when you actually include the if you actually look at the children one, it actually appears to strengthen the data. It appears to be stronger because look at this point right here, which strengthen this relationship, right? So it appears that the relationship between the variables is stronger for couples with children. So it appears that the strength of the relationship is greater for couples with children. Okay, all right, so that takes care of that one. So number 12, again, I think we have, let's see, one more question. Yep, so this is the last one, number 12. So one weekend, a statistician notices that some of the cars in the neighborhood are very clean and others are quite dirty. He decides to explore this phenomenon and asks 15 of his neighbors how many times they wash their cars each year and how much they paid in car repair costs. Okay, let me put this full screen here. So how much they paid in car repair costs last year. His results are in the table below. So we got the mean, standard deviation. The correlation for these two variables is r equals negative 0.71, and the scatter plot reveals a roughly linear relationship. Find the equation of the least squares regression line with y as the response variable. Okay, so this is a classic formula. Just calculate using the formula. So remember that y hat is a plus bx, and a to calculate b. This is from your AP formula sheet. The formula for b is r times sy divided by sx. And the formula on the formula sheet for the AP formula sheet, they give you the formula y bar equals a bar plus b x bar. And so in order to solve for, or not a bar, sorry, y bar equals a plus b x bar. In order to solve for a, you need to subtract b x bar, okay? So a is equal to y bar minus b x bar, okay? That's how you do that. All right, so let's calculate b first. We know that the r is negative 0.71, so all you gotta do is just plug and chug. The sy, this is sy, right? Because that's for y repair costs, and this is sx. So we get $323.50 divided by 3.78. And so we calculate this. Let's do this on the calculator and see what we get. So doing it on the calculator, you get negative 60.763. All right, and then we're going to take this and we're going to plug it in here to get A. So A equals, this is Y bar, this is X bar, 955.30 minus B is negative 60.763. So this is a double negative situation, okay? Times X bar is 6.4. So again, this turns positive, right? So really we're adding. And so A is about, let's do that on the calculator. So you get about 1,344.18 for A. So all you got to do at this point is now plug A and B into the y hat equation. So y hat equals A plus, now B is negative, so I'm going to put minus 60.763x. And there's your A plus BX. And there it is. That's all you had to do. Just plug in the numbers that you had. What percent of the variation in repair costs can be explained by the number of times per year a car is washed? So percent of the variation in repair costs can be explained. When you see percent of the variation in Y, that can be explained by X. When you see that that terminology used, you're looking for R squared. Okay, so they're looking for the coefficient of determination, which is R squared. Okay, so they're looking for R squared. So how do I get that? Well, they told us what R is, negative 0.71. So we got to take negative 0.71 and square it. So we'll do that on the calculator. And you get 0.5041 which is 50.41%. So it's 50.41% of the variation in the repair costs can be explained by the number of times per year a car is washed. All right. So based on these data, can we conclude that washing your car frequently will reduce repair costs? The answer to this is no. Correlation does not imply causation, okay? Correlation does not mean causation. All right, so I'm gonna since this was not a controlled experiment, there may be other variables that would cause the association. Such as, so we can do an example. Now, you don't necessarily have to include an example per se. You can say that there's confounding variables. There's other variables that would cause the association that would also lead to reduced repair costs, right? So what we want is a variable that reduces the repair costs, but is also associated with washing your car frequently. All right, so for example, if you wash your car frequently, then that means you are pretty good at maintaining your car, and so you might have other habits of maintaining your car, which therefore reduces repair costs, because maybe you maintain your car so well that you don't have to change, you don't have to do as many expensive items on the car because you're maintaining it, right? So such as other good car maintenance habits. That would lead to less repairs down the line. An example of good car maintenance habits are frequent oil changes, right? Things like that. All right, so again, bottom line, no, correlation does not imply causation, as long as you put that as your response, and then say that there might be other variables that could also cause this, impact. All right, guys, that's going to do it for the video. I hope you found this useful and informative, and as usual, I'll see you in the next one.